The universe is not what we thought it was. Science has mapped the stars, but the cosmos conceals deeper secrets that defy reality itself. Over 95% of everything is made of substances we cannot see or touch, dark matter and dark energy. This journey reveals 26 profound cosmic riddles that challenge the very foundations of modern astrophysics. You will discover why the universe is eerily silent and what causes stars to spin at impossible speeds. We will explore mysteries that question the nature of time and the ultimate fate of the cosmos. A tour of the greatest unsolved puzzles in existence. Everything you think you know about space is about to be turned upside down by enigmas that even Einstein's theories cannot fully explain. What does our cosmic ignorance reveal about our true place in the void? Our cosmic inventory reveals a ghostly ledger where most of the goods are simply missing. Think of the universe as a vast warehouse, filled with everything that exists. Yet when scientists count up all the stars, planets, and galaxies, they find less than 5% of the total stock. The rest, over 95% of the cosmos, is made of substances we cannot see or touch, dark matter and dark energy. This is the first and perhaps greatest riddle, the universe's missing matter. The ordinary stuff, called baryonic matter, is everything you have ever known, from the screen you are looking at to the most distant star. It is the tangible universe, and it is shockingly rare. The profound absence of what should be there is the mystery. We know this missing matter must exist because of its ghostly gravitational handiwork. We see its effects in the way galaxies spin far too quickly for the visible matter to hold them together. We watch as it bends the fabric of space-time, distorting the light from background galaxies into giant cosmic arcs, a phenomenon called gravitational lensing. This invisible scaffolding, as astrophysicist Priyamvada Natarajan describes it, is the framework upon which the visible universe is built. Yet for decades, despite searching in the deepest underground laboratories and the most powerful particle colliders, we have not directly caught a single particle of this dark matter. This forces a deep and unsettling question. How can we be so certain something is there when we cannot see it, touch it, or measure it directly in any way? The answer lies in the alternative, which is perhaps even more disturbing. If dark matter is not real, then our fundamental understanding of gravity, the force that literally holds the cosmos together, is wrong. We would need to rewrite the rules of physics itself. This fundamental gap in our knowledge is a haunting reminder that the universe is far stranger than we ever imagined, built upon a reality we are only beginning to perceive. Even our own spacecraft, sent to explore the void, began acting strangely. Billions of miles from home, the Pioneer 10 and 11 probes were inexplicably slowing down. It was as if an unseen hand was gently applying a brake, a tiny but persistent deceleration pulling them back toward the sun. For decades, this Pioneer anomaly represented a ghost in the machine, a nagging signal that something was wrong with our understanding of the cosmos. Launched in the 1970s, these robotic pioneers were on grand tours of the outer solar system. Yet as they journeyed farther into the black, their trajectories deviated from predictions by a minuscule amount, equivalent to just 1/10 billionth of the gravity we feel on Earth. To scientists, this was a massive discrepancy. Was it a flaw in Einstein's theory of gravity, a hint of new physics waiting to be discovered? Perhaps it was evidence of some unknown cosmic drag, or even the gravitational pull of unseen matter. The mystery captivated physicists and engineers for years, a puzzle whose solution seemed to lie just beyond our grasp. The eventual answer, however, was far more mundane, yet profoundly instructive. After meticulous analysis, the culprit was identified as anisotropic thermal radiation. In simpler terms, heat was radiating unevenly from the spacecraft's own systems. The electricity generated by their nuclear power sources produced heat, And as that heat escaped from one side of the probe more than the other, it created a tiny thrust, enough to produce the observed deceleration. The case was considered solved by most, a testament to engineering detail over revolutionary physics. Yet for some, a shadow of a doubt remains. Could a tiny fraction of that anomalous drift still be unaccounted for? This episode serves as a humbling lesson. It reminds us that the vacuum of space is not truly empty of surprises, and that our most precise instruments can behave in utterly unexpected ways when operating in the deep void for decades. Could other, subtler anomalies be affecting our deep space probes? Their secrets hidden within streams of telemetry data we have yet to fully decipher. That ghostly tug on our spacecraft was a mystery solved by careful analysis, but some cosmic signals defy all explanation. Decades before the Pioneer Anomaly, a radio telescope in Ohio was carrying out a routine sky survey. On a quiet August night in 1977, the silence of the data was broken by a single, staggering event. For 72 seconds, the Big Ear telescope recorded an intense, narrowband burst of radio waves, a signal so powerful and so perfectly aligned with the expected signature of an interstellar transmission that it stood out like a scream in the silence. When astronomer Jerry Amon saw the alphanumeric printout, he was so stunned he circled the sequence of characters and wrote one word in the red pen's margin: "Wow." That single word gave the signal its immortal name. The "Wow" signal came from the direction of the constellation Sagittarius, a region crowded with stars. It was concentrated in a band of frequencies near the hydrogen line, a logical choice for any civilization trying to announce its presence across the vast interstellar gulfs. It was the kind of signal the Search for Extraterrestrial Intelligence, or SETI, had been hoping to find, and then it vanished. Despite dozens of subsequent searches by larger and more sensitive telescopes, the signal was never heard again. It was a one-time event, a cosmic flash in the pan that has fueled debate for nearly half a century. Was it a fleeting hello from another world, a beacon that swept past our planet for just over a minute before moving on? Or was it a completely natural, if extraordinarily rare, astrophysical event? Scientists have proposed many explanations. Some suggested it was the hydrogen cloud of a passing comet, but the known comets in that area do not match the timing. Others wondered if it was a signal reflected off a piece of space debris. Yet none of these natural causes perfectly fits the data. The signal's unique properties, its strength, its frequency, and its transient nature, make it a perfect and profoundly frustrating enigma. It sits at the crossroads of our deepest hopes and our most rigorous skepticism. What if it was a message, and we simply heard only one word before the transmission ended or moved on? The "Wow" signal endures not as proof, but as a possibility. It is a constant reminder of the immense challenge in sifting a deliberate signal from the universe's chaotic background radio noise. It is the ultimate cosmic coincidence, or perhaps the one that got away, a tantalizing whisper that we are still trying to understand. The profound silence that followed the "Wow" signal echoes a much deeper cosmic question, one that has troubled scientists for generations. With hundreds of billions of galaxies, each home to billions of stars and countless planets orbiting within habitable zones, the sheer numbers suggest a universe that should be buzzing with intelligent life. The stage seems set for a crowded cosmic arena, yet when we listen, we are met with an unnerving quiet. This is the heart of the Fermi Paradox, famously crystallized by physicist Enrico Fermi during a casual lunch conversation in 1950. If they are out there, he asked, then where is everybody? The contradiction is staggering. The probability for other civilizations seems overwhelmingly high, yet we have no proof, no visits, and no signals we can verify. Proposed solutions to this silence are as fascinating as they are sobering. One chilling idea is the dark forest hypothesis. Picture the universe as a vast, dark woodland where every civilization is a hidden hunter. To make a sound to reveal your location is to risk annihilation by a more advanced and predatory species. In such a universe, the only safe strategy is absolute silence. Another possibility is the Great Filter, a hypothetical barrier so difficult to overcome that it prevents almost all life from progressing to interstellar travel. This filter could lie in our past, a rare evolutionary step we were lucky to clear, like the emergence of complex cellular life. Or, more ominously, it could await us in our future. Perhaps the technological maturity required for starfaring civilization inevitably leads to self-destruction through war or environmental collapse. The profound quiet could simply mean that intelligent life is vanishingly rare, or that it evolves into forms so alien that their signals and artifacts are completely unrecognizable to us. Are we the first intelligent beings to look up at the stars, a lonely forerunner in a young cosmos? Or are we the last, surrounded by the silent ruins of empires that rose and fell long ago? This paradox forces a deep introspection about our own species. Is the silence a warning, a challenge, or merely a reflection of our own cosmic immaturity? The answer, hidden in the void, may define the ultimate fate of humanity itself. The unsettling silence of the cosmos is mirrored by a pattern in its oldest light that seems to single us out. We gaze at the afterglow of the Big Bang itself, the cosmic microwave background, expecting a random tapestry of hot and cold spots from every direction. Instead, we find a strange and improbable alignment that cuts across the sky, a cosmic axis that eerily corresponds to the plane of our own solar system. Scientists, with a hint of dark humor, named this correlation the axis of evil. It is a label that underscores how deeply this finding disturbs our foundational beliefs. The cosmological principle is a pillar of modern science, stating that the universe is broadly the same in every direction and has no center or edge. This principle assures us that our view from Earth is not special, that any other observer in the cosmos would see a similar universe. The axis of evil directly challenges this comforting idea. The odds of such an alignment happening by pure chance are astronomically low, akin to throwing a dart blindfolded and hitting a single predetermined atom on the other side of the room. So what could possibly explain it? Some researchers argue it must be a statistical fluke, a ghost in the data that will vanish with more precise measurements. Others wonder if it is an artifact of our own making, a subtle error in how we subtract the foreground glow of our own galaxy from the primordial signal. But if it is real, the implications are staggering. It could mean that the universe is not isotropic after all, that it has a fundamental grain or direction imprinted upon it from a time before the Big Bang. Perhaps our local cosmic neighborhood is embedded within a vast, unseen structure that twists the fabric of reality on the grandest scales. This peculiar axis forces a profound question. Are we, against all odds, occupying a truly privileged position in the cosmos? Or is the universe itself far more complex and textured than our simplest models can describe? This cosmic coordinate system, whether a flaw in our perception or a feature of reality, leads us directly to another foundational puzzle: the very shape of the space we inhabit. This geometric puzzle brings us to the very shape of reality. We often imagine the fabric of space-time as a vast, flat plane, an infinite grid stretching into nothingness. But what if that grid is not flat at all? What if the entire universe is curved, warped into a shape we can scarcely comprehend? The geometry of the cosmos is not an abstract concept. It is the blueprint for its ultimate fate. Scientists describe three possible shapes, each with dramatic consequences. A positively curved universe would close in on itself like the surface of a sphere. In this cosmos, if you could travel in a perfectly straight line for long enough, you would eventually end up right back where you started. Parallel lines would slowly converge, and the angles of a triangle would add up to more than 180 degrees. This finite universe would eventually collapse in a fiery big crunch. A negatively curved universe would resemble a saddle, an infinite surface that bends away from itself. Here, parallel lines would diverge, flying eternally apart, and the angles of a triangle would sum to less than 180 degrees. Then there is the third option, a perfectly flat universe, where the rules of Euclidean geometry hold true and parallel lines never meet. For decades, the question of which shape describes our home remained one of cosmology's grandest quests. The answer came from the oldest light we can see, the cosmic microwave background. By meticulously mapping its subtle temperature variations, satellites have delivered a stunning verdict. The universe is flat to an astonishing degree of precision. The data leaves almost no room for curvature, a finding so exact it is both a triumph and a profound mystery. This perfect flatness is deeply unnatural. The standard Big Bang model predicts that any tiny kink or curve in the newborn universe would have been amplified over billions of years into a dramatically warped cosmos. The fact that we see a flat universe today implies something extraordinary must have happened in the first fleeting moments of existence. To explain this, physicists proposed a period of cosmic inflation, a moment of hyper-expansion when the universe ballooned in size by an unimaginable factor in a fraction of a second. This violent stretching would have smoothed out any primordial wrinkles, ironing the cosmos into the flatness we observe today. Yet inflation itself is a theory built on hypothetical energy fields, a necessary fix for a problem that otherwise seems unsolvable. The precise geometry is our destiny written in the sky. A flat universe, combined with the relentless push of dark energy, condemns the cosmos to an eternal, accelerating expansion. Galaxies will fly apart until their light can no longer reach us, and the universe will end not in fire, but in ice, a dark, cold, and lonely silence. Why is our universe balanced on this knife edge of geometric perfection? This flatness is a fragile condition, a clue that the initial setup of the cosmos was fine-tuned with impossible precision, pushing our inquiry back to the very genesis of everything. This perfect thermal equilibrium across the cosmos presents a paradox that cuts to the heart of causality itself. Look at the cosmic microwave background, the fossilized light from the universe's infancy. 2 points on opposite sides of this ancient sky have never, in all of cosmic history, been able to exchange a single photon. The distance between them is so vast that not even light, traveling since the first moment of time, could have bridged the gap. They are like two strangers stranded on islands separated by an uncrossable ocean, each completely isolated from the other. Yet when we measure their temperature, they are identical to within a breathtaking 1 part in 100,000. How can two regions that have never communicated possibly agree on the same exact temperature with such incredible precision? This is the horizon problem, and it suggests a cosmic conspiracy that defies our standard understanding of physics. Without any way to share information, these distant pockets of space should have evolved independently, developing wildly different temperatures and energies. The fact that they did not implies a connectedness in the early universe that we cannot explain. The leading solution is a dramatic one: cosmic inflation. This theory proposes that in the first fleeting fraction of a second, the universe underwent a growth spurt of unimaginable violence. A subatomic speck of space ballooned to a size larger than our entire observable universe in a time span so short it makes a blink seem eternal. This hyper-expansion would have taken a tiny, homogeneous patch and stretched it across the entire sky, ironing out any wrinkles and locking in that perfect, uniform temperature we see today. It is like blowing up a single, perfectly mixed balloon to the size of the Earth, every part of it sharing the same initial conditions. Yet for all its explanatory power, inflation raises even deeper questions. What was the engine that drove this incredible expansion, and what suddenly slammed on the brakes to end it? Physicists hypothesize an unknown energy field, dubbed the inflaton field, but we have no direct evidence it ever existed. The mechanism remains one of the most profound unsolved problems in physics. This riddle forces us to confront the very nature of cause and effect in the newborn cosmos, hinting at a primordial connectedness that challenges everything we thought we knew about the beginning of everything. This elemental recipe from the dawn of time has a single, glaring typo. In the universe's first 3 minutes, a frantic burst of nuclear fusion cooked up the primordial soup, a blend of hydrogen, helium, and a tiny sprinkling of lithium. The calculations for how much of each element should have been forged are breathtakingly precise. And for hydrogen and helium, the predictions match the observed abundances in the oldest corners of space almost perfectly. But lithium is the outlier. The amount of lithium-7 found in ancient stars is only about 1/3 of what the models insist should be there. It is as if the cosmic baker followed the recipe exactly, but forgot a crucial pinch of one specific spice. This is the lithium problem, a small but persistent crack in the otherwise solid foundation of the Big Bang theory. The evidence comes from the most pristine stellar laboratories we can find, ancient stars in the halo of our Milky Way. These stellar relics are thought to be time capsules, their atmospheres preserving the pure chemical composition of the infant universe, untouched by later generations of element-forming supernova. Yet when we analyze their light, the lithium signature is consistently and bafflingly low. Where did it go? Could our models of Big Bang nucleosynthesis be incomplete, missing some unknown nuclear reaction pathway that destroyed lithium as quickly as it formed? Some physicists speculate that exotic particles, certain types of dark matter that roamed the early cosmos, could have interacted with the primordial nuclei and broken lithium apart. Others propose a more straightforward, yet equally unsettling, idea. What if our understanding of stellar physics is flawed? Perhaps these ancient stars are not perfect time capsules after all, their churning interiors slowly dragging lithium down to their hotter cores where it could be burned away over billions of years. Each potential solution opens a new can of worms, challenging our grasp of nuclear physics, particle physics, or stellar evolution. This missing lithium is a ghost in the machine of creation, a whisper from the first moments that something in our grand narrative is subtly, yet undeniably, wrong. Why would the universe's foundational blueprint be correct for 2 elements and so conspicuously off for a third? This tiny discrepancy holds the potential to reveal entirely new processes that operated when the cosmos was just an infant, forcing us to question the very first chapter of our cosmic story. Our cosmic journey is not a random drift, but a determined flight toward a hidden destination. The entire Milky Way, along with our entire local neighborhood of galaxies, is racing through the void at a staggering speed of over 600 kilometers per second. We are being pulled irresistibly toward a specific point in the sky near the constellations Centaurus and Norma, a mysterious gravitational anchor astronomers call the Great Attractor. This is not a gentle nudge, but a powerful cosmic current dragging countless galaxies along with it. The source of this immense gravity lies in a frustratingly obscured part of the sky, a region nicknamed the Zone of Avoidance. Here, the thick dust, gas, and brilliant stars of our own galaxy's central plane create a visual wall, blocking our view of the universe beyond. It is like trying to see a distant city through a dense, permanent fog. For decades, this zone hid the true nature of the Great Attractor, forcing us to map this cosmic giant blind, using only the ghostly pull of its gravity on the galaxies we could see around it. We now know that a massive cluster of galaxies, the Norma cluster, sits at the heart of this region and contributes significantly to the pull. Yet even its immense mass is not enough to fully account for the phenomenal velocity of our own motion. The gravitational tug is far too strong, suggesting the Norma cluster is merely the brightest knot in a much vaster and darker structure, a supercluster of galaxies of almost unimaginable scale. This hidden behemoth is a stark reminder that our census of the universe is profoundly incomplete. What other colossal structures, these hidden architects of motion, are woven into the cosmic web just beyond our line of sight? The Great Attractor challenges our inventory of the cosmos, proving that the most powerful forces shaping our journey can remain invisible, their presence known only by the silent, relentless pull they exert on everything we can see. This relentless cosmic pull toward the Great Attractor is countered by a far more powerful and mysterious force operating on the grandest stage of all. Just over 2 decades ago, astronomers made a discovery that shattered a fundamental assumption about the cosmos. They confirmed that the universe's expansion is not slowing down, as everyone expected from the relentless pull of gravity, but is instead accelerating. It is as if every galaxy is being pushed apart by some invisible, repulsive energy woven into the fabric of space itself. This shocking revelation, which earned the Nobel Prize in Physics in 2011, introduced us to the dominant component of our universe, dark energy. Think of the cosmos as a loaf of raisin bread rising in an oven. For decades, we thought the dough was expanding, carrying the raisins, which are the galaxies, apart from one another, but that the expansion was gradually slowing as the dough stretched. The stunning truth is that the oven's heat is constantly increasing, making the dough rise faster and faster, pushing the raisins apart at an ever-quickening pace. This is the effect of dark energy, a force that constitutes about 68% of everything and completely overrules gravity on the largest scales. But what is it? The leading candidate is the cosmological constant, an idea Einstein once proposed and then discarded. This suggests that empty space itself possesses a fundamental energy density, a constant push that becomes more powerful as the universe expands and creates more empty space. Another idea is quintessence, a dynamic energy field that varies across space and time, a kind of fifth fundamental force. Or, most radically, could it be that Einstein's theory of general relativity, our gold standard for gravity, is simply incomplete and breaks down when applied to the vast emptiness between superclusters? The implications of this acceleration are as profound as they are bleak. We are headed for a future cosmologists call the Big Freeze or heat death. As the expansion accelerates, distant galaxies will be carried away from us so quickly that their light will no longer be able to reach us. Over trillions of years, every galaxy outside our local group will vanish from the observable universe, their light stretched beyond detectability. The cosmos will become a truly dark and isolated place. Any future civilization born in that era would look up at a nearly empty sky, with no evidence of the Big Bang or the vast cosmic web we see today. They would conclude the universe is a static, lonely island, completely unaware of the grand, vibrant cosmos that once existed. Why is the universe doing this? Why is the vacuum of space not inert, but filled with this repulsive force that defines our ultimate fate? The nature of dark energy is perhaps the most pressing question in all of physics, a fundamental mystery about the nothingness that makes up most of our reality. This profound conflict between our two greatest theories of physics strikes at the very nature of reality. A black hole presents a terrifying scenario for quantum mechanics, a framework built on the unshakable rule that information is never truly lost. You can burn a book, but in principle, a being with perfect knowledge could trace the smoke and ashes back to reconstruct every single word. Information is scrambled, not destroyed. Now imagine throwing that book into a black hole. Einstein's theory of general relativity paints a grim picture. Once an object crosses the boundary known as the event horizon, it is lost forever. its information seemingly erased from the universe as it is crushed into the central singularity. This is a fundamental violation, a cosmic deletion that quantum mechanics simply cannot allow. The conflict deepened with Stephen Hawking's revolutionary discovery. He realized that black holes are not entirely black. Due to weird quantum effects at the very edge of the event horizon, they slowly leak a faint glow of particles, now known as Hawking radiation. This process causes the black hole to gradually lose mass and, over eons, evaporate completely. The problem is that this Hawking radiation appears to be purely thermal, like the heat from a stove. It is random noise carrying no details, no fingerprints, no information about the stars, planets, or books that fell in. So when the black hole finally vanishes, what happened to all that quantum information? If it is truly gone, the foundations of physics are broken. This is the black hole information paradox. Proposed solutions are as mind-bending as the problem itself. One compelling idea is the holographic principle, which suggests that all the information about what falls into a black hole is not lost inside, but is instead encoded on its two-dimensional event horizon, like a cosmic DVD. The three-dimensional interior is a projection of that data. Another possibility is that the Hawking radiation is not random after all. Perhaps the information is imprinted onto the radiation in an incredibly subtle, scrambled way, a code so complex we have not yet learned to read it. Resolving this paradox is the key to unlocking a theory of quantum gravity, a single framework that can describe both the vast cosmos and the subatomic world. The fate of a single particle consumed by a singularity holds the secret to the fundamental laws that govern everything. The violent paradox of black hole evaporation pales before the raw, instantaneous power of a signal that can outshine a galaxy. In a fraction of a blink, a flash of radio waves from the deep cosmos can unleash more energy than our sun produces over 80 days. These are fast radio bursts, or FRB, and they are among the most explosive and least understood phenomena in the universe. Discovered only in 2007, these bursts are ghostly in their brevity, lasting mere milliseconds before vanishing back into the silence. They arrive from sources billions of light years away, meaning the cataclysm that created them happened when Earth was a barren rock. Their origins are a complete mystery, a cosmic whodunit written in pure energy. What makes them even more perplexing is their behavior. Some FRBs are one-time events, a single, spectacular cosmic firecracker. Others, however, repeat. They flash from the same patch of sky again and again, but in chaotic, unpredictable patterns that defy any simple rhythm. This has sent theorists scrambling. Could these flashes be the death cries of stars? The final violent moments as two ultra-dense neutron stars spiral into each other and merge. Perhaps they are the seismic shudders of magnetars, a type of neutron star with a magnetic field so intense it could strip the information from a credit card from half the distance to the moon. When these stellar corpses experience a starquake, a crack in their impossibly hard surfaces, they might release a torrent of radio waves that we detect as a fleeting burst. For the most powerful and unusual bursts, some even entertain the possibility of engineered origins, like powerful beams from interstellar light sails operated by advanced civilizations, though this remains a fringe hypothesis. The true power of these bursts, however, may not just be in their source, but in their journey. As an FRB travels across the universe, its different frequencies are slowed down by the thin fog of electrons that drifts between galaxies. By measuring this dispersion, astronomers can effectively weigh the invisible stuff the signal passed through. Each burst becomes a cosmic probe, charting the vast, unseen oceans of matter that fill the voids of space. Yet the central question remains: what natural engine can possibly concentrate such staggering energy and release it in a single, blindingly fast flash? These enigmatic signals are forcing us to confront a universe that is far more violently dynamic than we ever dreamed, where the darkness between the stars is punctuated by brilliant, fleeting mysteries we are only now learning to see. Beyond the violent flashes of deep space, our own solar system conceals a boundary that defies prediction. Far past the orbit of Neptune lies the Kuiper belt, a vast disk of frozen remnants left over from the planet's formation. This should be a realm of gently diminishing numbers, where icy worlds and chunks of rock become ever more sparse the farther you travel from the Sun. But that is not what we see. Instead, at a distance of about 50 astronomical units, the population of objects plummets. It is not a gentle fade, but a sudden cliff edge in space. This is the Kuiper Belt Cliff, a dramatic and unexpected boundary that suggests our solar system has a hard stop where none should exist. Why would this icy debris field simply end? One compelling theory points to the gravitational hand of an unseen giant. A hypothetical Planet 9, a world several times the mass of Earth orbiting far beyond this cliff, could be shepherding the orbits of these distant objects, clearing out a vast swath of space and creating this sharp drop-off through its immense pull. Another possibility reaches back into the Sun's infancy. Perhaps our star was born in a dense cluster with thousands of siblings, and a close pass by another young star long ago gravitationally stripped away the outer material of our Kuiper belt, leaving this abrupt frontier. The New Horizons spacecraft, which gave us our first close look at Pluto, is now voyaging through this very region. Its continued journey provides priceless data, scanning for faint, distant objects that could map the true shape of this cliff. Yet these bodies are incredibly dim and difficult to spot, meaning a definitive answer requires more powerful surveys of the sky's deepest reaches. This silent boundary is more than a curiosity. It is a fossil record of our solar system's past. Does it mark the scene of a forgotten stellar encounter? Or is it the ongoing work of a hidden world whose gravity sculpts the outer dark? The cliff stands as a testament to the fact that even in our own cosmic backyard, the final map remains unfinished. Even the orderly dance of our solar system holds a subtle, off-kilter rhythm. While the planets trace out their orbits in a remarkably flat disk, the Sun itself spins on a tilted axis, cocked at a 6-degree angle to the plane of its children. This solar tilt is a quiet anomaly that should not exist. If our entire system coalesced from a single, spinning cloud of gas and dust, conservation of angular momentum dictates that the Sun's spin should align perfectly with the orbits of the planets. The fact that it does not means our history is written in this gravitational slant. What could have pushed our star off its axis? One dramatic possibility is a stellar intruder. In the solar system's violent infancy, a rogue star may have wandered too close, its gravitational pull giving the infant Sun a slight nudge that set it spinning askew. This celestial billiard shot would have been a fleeting event, but its fingerprint would be permanently etched into our star's orientation. Another, more persistent culprit could be the hypothetical Planet 9. If this unseen giant truly orbits far beyond Neptune, its immense gravitational influence, exerted over billions of years, could have slowly torqued the entire solar system, leaving the Sun with this telltale tilt. Or perhaps the answer lies not in external forces, but in the internal structure of the primordial cloud itself. Asymmetries in the distribution of mass within that early nebula, or powerful magnetic fields twisting the infant star, could have generated the misalignment from within. Each theory paints a different picture of our origins, from a dramatic stellar encounter to the slow, grinding pull of a hidden world. This 6-degree tilt is more than a geometric curiosity. It is a fossil pointing to a chaotic and dynamic past, a reminder that our seemingly stable cosmic neighborhood was forged in a much wilder nursery. This ghostly halo extends the Sun's dominion to the very edge of interstellar space. Picture a sphere of frozen wanderers so distant that the sun is merely a bright star in their black sky, a reservoir of ancient ice stretching nearly a light year into the void. This is the Oort Cloud, the ultimate frontier of our solar system and its most elusive feature. We have never directly seen a single object within it, for these icy bodies are too small, too dark, and too incredibly far away for any telescope to spot. Their existence is a ghostly inference, a deduction made from the dramatic arrivals of long-period comets. These icy visitors, like the famous Hale-Bopp, swoop in from every direction on orbits that take thousands or even millions of years to complete. Their paths point back to a vast, spherical shell, the only source that could explain such random and deeply rooted journeys. This cloud is thought to be the frozen leftover building material from the solar system's formation, a cosmic junkyard where planetesimals were tossed into the deep freeze by the gravitational kicks of the young giant planets. But its current shape is not solely the work of our Sun. The gentle but persistent gravitational tug of the Milky Way itself, the galactic tide, constantly kneads this distant cloud, while occasional close passes by other stars send a shower of comets tumbling inward toward the planets. This makes the Oort Cloud a dynamic interface, a place where the gravity of our solar system meets the influence of the entire galaxy. Its hypothetical existence forces a profound question. How much of our cosmic model is built upon such ghostly evidence? On structures we are convinced must be there but have never laid eyes upon. Confirming this distant halo would complete our map of the Sun's gravitational domain, turning a theoretical shadow into a tangible, if unreachable, place. It holds the pristine record of our system's birth, but until we can peer into that profound darkness, it remains the solar system's final and greatest unseen realm. The orderly spin of a spiral galaxy is a cosmic dance choreographed by gravity. Common sense tells us that stars farther from the galactic center, like the outer planets in our solar system, should orbit more slowly. Yet when astronomers measured the velocities of stars in these vast pinwheels, they found something astonishing. The orbital speed does not drop off with distance, it remains stubbornly, impossibly flat. Stars on the fringes whirl around just as fast as those near the brilliant core. This is the galactic rotation problem, and it shatters our classical expectations. If what we see is all there is, these outer stars should be flung into the intergalactic void by their own speed. The fact that they are not means something invisible is holding them in place. This was the first compelling clue for dark matter, the ghostly gravitational glue that forms an immense, unseen halo around every galaxy. A halo that contains far more mass than all the stars, gas, and dust combined. But what if the answer is not an invisible substance, but a flaw in our understanding of the force itself? A bold alternative called modified Newtonian dynamics, or MIND, suggests that gravity behaves differently at the extremely low accelerations found in the vastness of galactic space. It is not that extra matter is pulling on the stars, but that the rules of the pull change when the pull becomes incredibly weak. For some individual galaxies, MIND predictions match the flat rotation curves remarkably well. Yet this theory faces its own profound challenges. It struggles to explain the intricate gravitational dances within massive galaxy clusters or the precise way light bends around them, observations that dark matter handles with ease. So we are left with a fundamental choice. Is the cosmos filled with a mysterious, dominant form of matter that refuses to interact with light? Or must we rewrite the laws of physics that have guided us since Newton? The silent, steady spin of every spiral galaxy is a direct challenge, a universal rhythm that whispers we are still missing a crucial piece of the cosmic puzzle. This stellar enigma began with a flicker of data that defied all known patterns. Among the hundreds of thousands of stars monitored by the Kepler Space Telescope, one stood out as profoundly broken. KIC 8462852, better known as Tabby's star, displayed a light curve unlike any other. Instead of the gentle, rhythmic dips caused by orbiting planets, its brightness would plummet erratically by as much as 22%, a staggering amount of missing light. Imagine if our own sun suddenly dimmed by a fifth for days or weeks at a time. A change so drastic it would be visible to the naked eye across the galaxy. This was not the signature of a simple planet, which typically blocks less than 1% of a star's light. It was the signal of something vast, something complex, and something utterly mysterious orbiting this distant sun. The most tantalizing, though least likely, explanation captured the public imagination. Could this be evidence of an alien megastructure? A vast swarm of energy collecting panels known as a Dyson sphere, in the process of being built around the star. This hypothesis, while thrilling, was always a last resort, the kind scientists turned to only after exhausting all natural explanations. And indeed, follow-up observations painted a different picture. Detailed analysis of the starlight revealed that the material causing the dimming was not solid and opaque, like a giant structure would be, but was instead composed of fine, heterogeneous dust. The star's light was being blocked by a chaotic, uneven cloud of debris. So what natural catastrophe could produce such a colossal and messy veil? Astronomers have proposed a cataclysmic event, such as the gravitational disintegration of a moon or a planet, creating a vast, swirling field of fragments and dust that passes in front of the star in irregular clumps. Alternatively, a giant swarm of comets stirred up by a passing star could be on a chaotic orbit, but the scale required is almost as mind-boggling as the megastructure itself. The true nature of this cosmic debris cloud remains an active puzzle. The investigation of Tabby's star stands as a powerful modern parable. Its discovery was fueled by the sharp eyes of citizen scientists sifting through public Kepler data, a beautiful collaboration between curious amateurs and professional astronomers. It reminds us that the universe is still full of wild, unexplained phenomena that challenge our categories. What other strange stellar behaviors are hidden in the mountains of data we have already collected, waiting only for a curious mind to notice the anomaly? The universe's most violent events fire invisible bullets across the cosmos. These are ultra-high-energy cosmic rays, subatomic particles like protons and atomic nuclei that race through the void at nearly the speed of light. Their energy is almost incomprehensible, millions of times greater than anything we can produce in our most powerful particle accelerators like the Large Hadron Collider. A single one of these particles can carry the kinetic energy of a well-thrown baseball, all packed into a fragment of an atom smaller than you can imagine. They are the fastest, most energetic things we know of in the universe, and we have no clear idea what creates them. This mystery is over a century old, dating back to when scientists first realized our atmosphere was constantly being bombarded by radiation from deep space. The central puzzle is not that they exist, but what cosmic engine can possibly launch them. On Earth, we need machines miles long to accelerate particles to a fraction of this energy. What natural process out there is so powerful, so efficient, that it can do this on a galactic scale? The prime suspects are the most extreme objects we know. Supermassive black holes at the hearts of active galaxies, wherein falling matter is torn apart and shot out in colossal jets. The explosive deaths of massive stars in gamma-ray bursts, the most luminous events since the Big Bang. Or the expanding shock waves from supernova remnants, which might act as natural particle accelerators for millennia. The challenge is that these cosmic bullets do not travel in straight lines. As they cross the vast distances between galaxies, their paths are twisted and bent by the weak but pervasive magnetic fields that fill interstellar space. By the time one finally strikes the upper atmosphere, creating a shower of secondary particles we can detect, it is impossible to simply trace its path back to its source. It is like trying to find the origin of a single, specific raindrop in a hurricane. The Pierre Auger Observatory in Argentina uses an array of 1,600 water tanks spread over an area the size of Rhode Island to catch these rare, high-energy events. By analyzing the patterns, scientists have found a statistical correlation, a hint that the very highest energy rays seem to come from areas of the sky with certain types of active galaxies. But a correlation is not a smoking gun. We have not yet pinned down the exact mechanism within those galaxies that can focus and fire these particles with such unbelievable force. Are we missing a whole class of cosmic catastrophe, an event even more violent than the ones we have catalogued? Each of these particles is a messenger, carrying encrypted information about the conditions in the most hellish environments in existence. Decoding their origin is not just about solving a century-old riddle. It is about using nature's own artillery to probe the fundamental limits of physics in a realm we can never hope to visit. Far from the chaotic explosions of dying stars, another cosmic farewell unfolds with geometric perfection. The Red Rectangle Nebula is a masterpiece of stellar symmetry, a glowing hourglass of gas and dust ejected from a dying binary star system known as HD 44179. Its name comes from its appearance through our telescopes, a roughly rectangular shape painted in a deep, crimson hue. But the true mystery of this object is not its form but its light. When scientists break that red glow into its constituent colors, creating its spectrum, they find a set of bright, sharp emission bands that defy all identification. These are the unidentified infrared bands and the extended red emission, spectral signatures that act as a precise chemical fingerprint for molecules we have never seen. The leading suspects are complex organic molecules known as polycyclic aromatic hydrocarbons, or PAHs. These are sprawling, carbon-rich compounds, essentially the sooty leftovers from incomplete combustion. On Earth, they are found in charred barbecue grills and diesel exhaust. In space, they are thought to be common, the building blocks for more complex chemistry. Yet when we compare the precise spectral lines from the red rectangle to any PAH molecule we have created or found on our planet, nothing matches perfectly. It is as if we have a suspect's fingerprint on file, but it does not belong to any known person in our database. This nebula is a cosmic chemical forge, operating under conditions we cannot easily replicate. Its stunning bipolar structure, a result of the intricate dance between its two central stars, creates a unique environment where these exotic carbon compounds can form and be illuminated. The symmetric jets act like a laboratory chamber, confining and shaping the chemistry happening within. This makes the red rectangle more than just a pretty cosmic picture. It is a natural experiment showing us the types of complex molecules that are created in the final stages of a star's life. The profound question is what these unidentified bands represent. Are they entirely new forms of carbon-based matter? Structures more complex than any we have imagined? Could they be the precursors to the very molecules that eventually lead to life, forged in the funeral pyres of stars and scattered across galaxies by stellar winds? The red rectangle's enduring spectral riddle reminds us that the universe is not just physically wild, but chemically inventive, writing its recipes in a light we are still learning to read. Storms rage across Saturn's northern pole, but they rage with an impossible geometry. A colossal hexagon, wider than two Earths placed side by side, encircles the planet's north pole. This is not a fleeting atmospheric fluke. First glimpsed by the Voyager probes in the 1980s, it was still there, spinning in perfect synchrony with the planet's rotation, when the Cassini spacecraft arrived decades later. It is a six-sided jet stream, a highway of wind with walls of cloud that plunge deep into the atmosphere, a polygon etched onto a spinning ball of gas. How can a fluid, chaotic system like a planetary atmosphere lock itself into such a rigid, geometric shape for generations? The secret lies in the physics of spinning fluids. Think of stirring a cup of coffee. You see a central depression form, a vortex. Now imagine that vortex is a planet, and the different layers of your coffee are atmospheric bands moving at thousands of miles per hour. The hexagon is a standing wave pattern, a stable vibration in the fluid atmosphere, born from the shear between these rapidly moving jet streams. It is the same principle that creates the distinct notes in a musical instrument, a resonance frozen in place by Saturn's furious rotation. Scientists have recreated smaller versions of this phenomenon in labs, spinning barrels of fluid to watch polygons emerge. Yet scaling this up to a planet is a monumental challenge. Saturn's internal heat, its deep weather layers, and the precise wind gradients all play a part in tuning this atmospheric instrument to play a single hexagonal note. So why a hexagon? Why not a pentagon or an octagon? The shape may be the most stable configuration for the specific speeds of Saturn's polar winds, the form that dissipates energy most efficiently in that chaotic environment. It is a natural outcome, a preferred pattern for that particular planetary system. This beautiful, enduring structure is a lesson in order emerging from turbulence. It proves that the universe, even in its most violent and dynamic states, has a hidden preference for patterns, for stability hidden within the storm. Our cosmic inventory of chemical mysteries finds a profound echo in the history of our own night sky. The moon's serene presence belies a violent and puzzling origin. It is far too large compared to Earth, a planetary companion on a scale seen nowhere else in the inner solar system. Its orbit is also subtly askew, tilted about 5 degrees from our equator. This configuration is a direct challenge to our best story of its birth, the giant impact hypothesis. According to this dramatic tale, a Mars-sized world named Theia once smashed into the infant Earth, vaporizing a colossal amount of material that later coalesced into our moon. The problem is in the fine print of the simulations. When scientists model this cataclysm, the resulting moon often ends up orbiting neatly in Earth's equatorial plane, not in the tilted path we observe today. Something must have given the moon a gravitational nudge after its formation. Could other, smaller moons have formed alongside it, their chaotic interactions over millions of years slowly pushing our moon into its current pose? Or did the steady, persistent tug of the sun's gravity, acting over eons, torque its orbit into this slight slant? The chemical evidence deepens the mystery. The rocks brought back from the lunar surface are strikingly similar to Earth's own, their isotopic fingerprints nearly identical. For the impact theory to hold, this implies a degree of mixing between Theia and the young Earth so thorough that it completely erased the intruder's chemical identity, a scenario that requires very specific and potentially unlikely conditions. Was Theia, by chance, already a chemical twin to our own planet? Or does the model need a fundamental revision, perhaps involving a much higher energy impact that created a thoroughly blended vapor cloud from which both Earth and Moon condensed? Each new sample retrieved by lunar missions is a piece of this primordial puzzle. The quiet moon hanging in our sky is a living relic of cosmic violence, its tilted path a silent question about the chaotic forces that shaped our world and set the stage for life itself. Our cosmic yardstick is giving us two different measurements, and the discrepancy is tearing at the seams of modern cosmology. This is the Hubble Tension, a stubborn rift between how we measure the universe's current expansion rate. On one hand, we use a cosmic distance ladder built from pulsating stars called Cepheid variables, and the brilliant flash of supernova in our galactic neighborhood. These are our local markers, giving us a present-day value for the Hubble constant. The results are precise and seem robust. Yet when we look to the ancient universe, to the fossilized light of the cosmic microwave background mapped by the Planck satellite, we get a different answer. The Planck data allows us to extrapolate what the expansion rate should be today based on the conditions of the infant cosmos. Both methods are pillars of modern science, meticulously checked and rechecked. But they do not match. The local measurements suggest the universe is expanding a few percent faster now than the primordial data predicts. A few percent may sound trivial, but in the realm of cosmology, where measurements are exquisitely precise, it is a glaring chasm. With every improvement in our telescopes and instruments, this gap has not closed. It has only widened, solidifying into a genuine crisis. So what is causing this rift? The most conservative explanation is an unknown systematic error, a subtle flaw in how we measure cosmic distances that we have not yet caught. Perhaps our understanding of Cepheid stars or supernova has a hidden blind spot. But if the error is not with our instruments, then it must be with our theories. This tension could be the first direct evidence that our standard model of cosmology, known as lambda CDM, is incomplete. It might be hinting at exotic new physics operating in the universe's first moments. One compelling idea is early dark energy, a transient form of the repulsive force that may have surged briefly in the cosmos's infancy before fading away. This extra push would have altered the initial conditions just enough to explain why the universe today is expanding faster than our models expect. Other possibilities include strange types of neutrinos that carry more mass or interact in ways we do not yet understand. The Hubble tension is more than a statistical anomaly. It is a potential crack in the foundation. It forces us to ask whether we have fully understood the journey from the Big Bang to the present day. Is the universe trying to tell us that its history is even richer and more complex than we have dared to imagine? Deep within the galactic core, a mysterious light refuses to be explained. Scientists mapping the gamma-ray sky have found a persistent and puzzling glow emanating from the center of our Milky Way, a signal that outshines all known astrophysical sources. This is the galactic center excess, an unexplained fountain of high-energy photons that has become one of the most compelling puzzles in modern astrophysics. The usual suspects do not fit the crime. It cannot be fully accounted for by the collective hum of spinning neutron stars known as pulsars, or by the expected radiation from cosmic rays slamming into clouds of interstellar gas. The signal is just too bright, its pattern too distinct. This has led to a thrilling and controversial hypothesis. What if this gamma-ray glow is the long-sought-after signature of dark matter? The theory is that weakly interacting massive particles, or WIMP, the leading theoretical candidates for dark matter, could be gathering in the dense core of our galaxy. There, under the immense gravitational pull, these particles would collide and annihilate each other, transforming their mass into pure energy and releasing the very gamma rays we detect. It is a beautiful, elegant idea, a potential solution to two great mysteries at once. Yet the cosmos rarely offers easy answers. Other explanations are equally plausible. This excess could be coming from a vast, hidden population of ancient, rapidly spinning pulsars that are too faint for our telescopes to pick out individually. Their combined light could mimic a smooth, glowing excess, or it could be the fossil imprint of a past starburst period, a frenetic era of star formation that left behind a specific kind of radioactive fallout. The key to solving this lies in the precise character of the glow, its spatial distribution and its energy spectrum. A signal from dark matter annihilation would look very different from a signal produced by a crowd of pulsars. So far, the data remains stubbornly ambiguous, a tantalizing but blurry picture. Is this the moment we finally glimpse the invisible skeleton of the cosmos? Or are we simply seeing a new type of astrophysical chorus from objects we have not yet learned to identify? This unresolved glow at the heart of our galaxy is a beacon, and its true nature could either illuminate the dark universe or reveal an entirely new chapter in galactic astrophysics. A visitor arrived without warning, a cosmic messenger from a star system far beyond our own. In 2017, telescopes in Hawaii detected an object accelerating through our solar system on a trajectory so hyperbolic it could only have come from interstellar space. They named it Oumuamua, Hawaiian for scout, and it was unlike anything we had ever seen. Its path was not bound by the sun's gravity, it was just passing through. This alone was historic, the first confirmed tourist from another star. But its strangeness only deepened with every observation. Its brightness varied dramatically as it tumbled, suggesting a shape that was not round, but extraordinarily elongated, perhaps 10 times longer than it was wide. A spinning cosmic cigar or a pancake tumbling through the void. Then came the real puzzle. As it sped away, its acceleration could not be explained by gravity alone. Something was giving it an extra push. For comets, this is common, caused by outgassing. As the sun heats a comet's icy surface, jets of gas act like tiny thrusters. But Oumuamua showed no visible coma, the fuzzy cloud of gas and dust that surrounds an active comet. It appeared as a bare, rocky shard in our telescopes, a silent, dark object with a hidden engine. The absence of a clear, natural explanation opened the door to a thrilling, if controversial, idea. Could this non-gravitational push be light pressure from the sun itself, acting on a vast, thin structure? Was Oumuamua a derelict light sail, a piece of alien technology drifting through the galaxy? This hypothesis, while captivating, was always a last resort. Science demanded a natural explanation, and subsequent research has provided compelling candidates. The object could have been a chunk of solid nitrogen ice, similar to the material found on Pluto's surface. As the sun warmed this exotic ice, it would have sublimated directly from solid to gas, creating the necessary thrust without producing the dusty coma typical of water-ice comets. Other ices, like solid hydrogen or carbon monoxide, have also been proposed. Each of these theories can explain the acceleration, yet they leave other questions unanswered. Where does such a large, pristine chunk of nitrogen ice form, and how is it ejected from its home system? The true nature of this interstellar scout remains shrouded in mystery, a single data point from the vast galactic ocean. Its brief, puzzling passage reminds us that our solar system is not an island, but a crossroads in a busy galactic highway, constantly swept by material from other stars. Future observatories will undoubtedly spot more of these visitors, and with more advanced warning, we may even send probes to intercept one. Oumuamua was our first glimpse of this hidden traffic, a silent, enigmatic rock that challenged our categories and expanded our sense of cosmic neighborhood. What other strange travelers are sailing the void between the stars, carrying the untold histories of alien suns? The profound quiet of the cosmos may not be an absence of voices, but a failure of our perception. We listen for radio signals, expecting to hear something like ourselves. But a civilization just a few centuries more advanced than ours might have moved beyond such primitive beacons. They could have transitioned to a post-biological existence, their consciousness uploaded into super-intelligent machines or dwelling within intricate simulated realities that leave no trace on the electromagnetic spectrum. Their conversations might be conducted through quantum entanglement or in dimensions we cannot access. Their artifacts and energy use so efficient they are indistinguishable from the background hum of the universe. Another possibility is as humbling as it is profound, the zoo hypothesis. In this scenario, Earth is a designated wilderness area, a galactic preserve where a more advanced civilization observes us from a respectful distance, enforcing a strict policy of non-interference to allow our culture and technology to develop naturally. The silence would then be a deliberate choice, a one-way mirror we have not yet learned to see through. Or perhaps the true barrier is time itself, The lifespan of a technological civilization might be tragically short, a fleeting flash in the cosmic night, while the windows for two such flashes to overlap in the same galactic neighborhood are vanishingly small. We could be like mayflies, born in the morning and gone by the afternoon, trying to spot another mayfly on a distant continent. The next generation of observatories, like the Square Kilometre Array, will soon scan millions of stars, not just for radio signals but for the technosignatures of these advanced states, like the waste heat of mega-structures or the light pollution of a planet-wide city. This immense effort will either transform the great silence into the great discovery or deepen the mystery to its absolute limit. Are we listening for the wrong things, searching for echoes in a universe that has long since moved on to a different language? This enduring riddle forces a final, introspective look at our own trajectory. Will our own civilization, if it survives, become one of these silent, invisible entities, leaving behind the noisy radio age to join the cosmic background, forever undetectable to the next curious species gazing up at their stars? Our quest for cosmic truth inevitably shrinks to a scale beyond imagination. We have journeyed from the vast galactic horizon down to the very fabric of reality itself, and here we find the final, foundational riddle. The smooth, continuous stage of space and time, the very setting for every cosmic event, may be an illusion. According to our best theories, if we could peer down to the universe's smallest possible level, the Planck scale, the serene geometry of Einstein's cosmos would dissolve into a chaotic, turbulent sea. This is the realm of quantum foam, a frothing, bubbling ferment where the concepts of here and there, before and after, simply cease to have any stable meaning. In this domain, tiny virtual particles and wormholes would constantly blink in and out of existence, churning the void into a probabilistic frenzy. The implications of such a grainy reality are staggering. A photon traveling for billions of years from a distant gamma ray burst would, in effect, be bouncing across this microscopic foam. Over such an immense journey, these tiny, random bumps could slightly blur the image or cause subtle shifts in the light's properties. It would be like observing a distant mountain through a heat haze, but a haze woven into the structure of space itself. Our most powerful telescopes today are not yet sensitive enough to detect this predicted blurring, leaving this ghostly texture just beyond our reach. The hunt for quantum foam is the driving force behind the single greatest quest in modern physics, the unification of general relativity with quantum mechanics. We need a theory of quantum gravity to navigate this realm, a single rulebook that governs both the immense curvature of a black hole and the probabilistic dance of the subatomic world. Competing visions offer radically different pictures of this fundamental layer. String theory proposes that the ultimate constituents of reality are not point particles but unimaginably tiny, vibrating loops of energy. Their different resonant frequencies would give rise to every particle and force in nature, with space-time as their stage. Loop quantum gravity, in contrast, suggests that space itself is not continuous but is woven from a network of finite, discrete loops, a fabric of individual threads. In this view, space has a fundamental atomic structure. Both theories, and others like them, aim to answer the profound question of whether space and time are fundamental, or if they are emergent properties that arise from a deeper, more basic quantum reality, much like temperature emerges from the frantic motion of molecules. Are the dimensions we move through and the time we experience simply a collective illusion, a macroscopic average of a hidden, granular truth? This final riddle challenges not just what we know, but the very framework through which we perceive existence, suggesting that the cosmos is built upon a foundation far stranger than the void. Humanity's quest to decipher the cosmos is a story written across millennia. Long before telescopes, ancient cultures mapped the heavens with naked eyes, weaving intricate myths to explain the wanderings of planets and the sudden appearance of comets. They saw celestial dramas and divine messages in patterns we now chart with mathematics. The scientific revolution transformed this relationship, replacing gods with gravity and myth with mathematics. Galileo's telescope revealed moons orbiting Jupiter, proving Earth was not the center of all things. Newton's laws gave us the equations to predict planetary motion, turning the sky into a clockwork universe. Each generation faced its own profound cosmic puzzles. The perplexing retrograde motion of Mars, which once demanded complex celestial spheres, was elegantly explained by the heliocentric model. Fuzzy patches of light known as nebulae were eventually resolved into vast clouds of gas and dust, the cradles of new solar systems. Even the source of the sun's immense power, a mystery for centuries, was unlocked as nuclear fusion. Every solved riddle did not mark an end to inquiry, but a new beginning. It built a stronger foundation from which to ask more daring, more fundamental questions. The 26 profound riddles we grapple with today are not evidence of our failure, but of our progress. They represent the expanding frontier of our curiosity, the new horizon revealed once the old one was reached. Just as the mystery of the Martian loop was solved not by magic, but by patient observation and a new model of the solar system, so too might our current enigmas yield to the next generation of brilliant minds and powerful instruments. The Great Attractor and the nature of dark energy are the modern equivalents of those ancient celestial puzzles, challenges that will inevitably redefine our place in the cosmos once more. Our journey of cosmic understanding is an endless, evolving story, a conversation with the universe where every answer whispered back only reveals a deeper, more beautiful question waiting in the dark. These 26 cosmic riddles defy simple explanation, from the ghostly pull of dark matter to the quantum foam of spacetime. Each one challenges a fundamental pillar of our scientific worldview, revealing cracks in our understanding of gravity, time, and the very fabric of reality. These are not mere gaps in knowledge waiting to be filled with more data. They are profound puzzles that hint at a universe far more complex, strange, and wonderful than we ever anticipated. They force us to confront the humbling truth that our current laws of physics are a starting point, not a final answer. As Carl Sagan famously reflected, somewhere, something incredible is waiting to be known. This exploration stands as a powerful reminder that curiosity is our greatest tool in the face of the unknown. The universe's greatest mysteries are not walls to stop us, but invitations to look deeper, think bigger, and continue the search with renewed wonder. We encourage you to share which of these cosmic riddles fascinates you most in the comments below, and to subscribe for more journeys to the edge of understanding. The cosmos is not finished surprising us yet, and the next great discovery is waiting just beyond the light of our current